All right, so at 10:01, I'm gonna get started and we'll start going through some material in just a moment. But before I do, I want to remind everyone that there are some homeworks due this Friday at 5. So make sure you get those done, particularly the ones here on the algebraic modeling. So the algebraic modeling homeworks due Friday at 5. You can see the homeworks there. But so all of the ones from the algebraic modeling are due Friday at 5. Oh, the remaining ones, I should say. Last Friday, we had homework due too. We had this one. But the 3 types of models, homeworks are due then. All right, so let's go to the last part. Now, this is the bonus part of the algebraic models, okay? But it's a natural thing to do right now because we just got done dealing with rational models. And I said the type of rational models that we are going to be dealing with are the ones that I will give to you, all right? So you're not going to create rational models. And in the same breath, we could say, well, could we have been given any models? Some model that we looked up on Google, as it has been well known and previously known, all right? So maybe somebody already developed a model and it's out for the public, or maybe it's a very famous, physics equation or a famous geometry equation that we typically don't think of. For instance, if you're talking about the area of a rectangle, it's the length times the width of the rectangle, right? When you start out doing math, you're given a lot of these types of equations, right? And they're just given to you. So like I said, physics, this happens, geometry, this happens. And even a lot of the pricing calculations, like the tax models that we were given, the interest models that we were given. Now we kind of justified our interest models, but still a lot of the price calculations we were given. All right. So let's take one from geometry. Let's look at the volume of a pyramid. Well, if you looked up the volume of a pyramid with a square base, the volume of that pyramid would be given to you by the following equation. S squared times H divided by 3. Now, S there stands for side length. H stands for the height of the pyramid. And V obviously stands for value. So again, this is a pyramid with the square base. So you go look up that formula. You could derive that, but might as well just look it up. Or somebody gives it to you. And once you're given this algebraic formula, it is a model for the value of that pyramid. And therefore, we can ask the same types of questions we did in the previous sections. We can say, for instance, if the base of a pyramid is square with sides of length 30, that's 30 feet, and height of 20 feet. What is the value? Okay. Since I've already been given that model, all I have to do is plug in the right numbers into the right variables. In this case, since we're dealing with side lengths of 30, the 30 goes in for the S. The height of 20. 20 goes in for the H. And then dividing by 3. That's something I can just type into my calculator. So I grab my calculator and I put 30 squared times 20 and then divide by 3. I get 6,000. So the volume of that pyramid is 6,000. Now, I'm not going to ask you to figure out the labels or anything like that, but because we have feet times feet times feet, it turns out a volume is in cubic feet. All right, so the volume is 6,000 cubic feet. You guys know what it means to be a cubic foot? You guys know what that measurement is? It's a, think of it as a box, a block. If I had drawn this better, it would look better. So okay. So it's a block that's a 1 foot by 1 foot by 1 foot block. That's what a cubic foot is. It's a cube that's 1 foot by 1 foot by 1 foot. All dimensions. Cubic. So a cubic foot of anything is things that can fit into a 1 foot by 1 foot by 1 foot block. Right? So it's a cube where all the side, the length, the width, and the height are all 1 foot. That's what it means to be a cubic foot. So it says 6,000 cubic feet. It means 6,000 of those blocks would fit inside the pyramid if you cut them up and reorganize them. Types of things. Doesn't necessarily mean it's a block shape, but if you cut them up and reorganize them, that's what you get. The Great Pyramid of Giza is also a pyramid whose base is a square, or very, very close to a square. Its side lengths are 230.4 meters, and its height is 146.3 meters. I want you to use the formula we just did to calculate the value. of the Great Pyramid of Giza. All right. So let's take a look at this one. Side lengths are 230.4. So I put that in for my S. So put that in, square it, multiply by 146.3 because I put that in for my H, and then divide by 3. Now, when you do that, you end up with 258.8737 point about 54, rounding it to 2 decimal places. So that's a value of over 2.5 million. And since these are in meters, this would be cubic meters. Also, a lot of people will write cubic meters as an M with an exponent of 3. M is the shorthand for meters. 3 is the shorthand for cubic. And the reason that 3 is a shorthand for cubic is because you have 3 dimensions in the cube, right? Length, width, and height. So cubic meters, M cubed, same thing, right? That's the shorthand notation for cubic meters. So if you see that on the labeling, that's what it's standing for. Okay. By the way, that's a gigantic value. That many cubic meters of rock and granite and all that stuff is just mind blowing. It's a lot of stuff. So that's one from geometry. That's an example from geometry. Here's an example from physics. Centripetal force is the force that keeps a body in a curved path. The magnitude of that force is given by M times V squared divided by R. M is the mass of the object that's moving around. V is the velocity of the object. And R is the radius that it's going around, right? So it keeps the body in a curved path. So the mass times the velocity divided by the radius. The mass times velocity squared divided by radius. Does that make sense? We kind of know it. Just draw a very quick picture of the centripetal force. If you have something spinning around in a circle, some object, right? How fast it's spinning, that's your velocity. The mass of the object, your m, and then the radius, the point it's spinning around, is your r. Okay? And so those things combined in that way give you centripetal force. Okay. So you probably guess what we're going to do. We're going to say if the velocity of an object is 40 meters per second, the radius is 10 meters, and the object has a mass of 50 kilograms, what's the centripetal force? Calculate this on your own. All right. So mass was 50 kilograms. Velocity was 40 meters per second. And the radius was 10 meters. So we just typed that in. 50 times 40 squared divided by 10. Doesn't matter. It matters that you are multiplying the 50 times this fraction. But if you want to put it in parentheses or not put it in parentheses, you could put a divide sign without the parentheses. It's not a big deal. And the force comes out to be 8,000. Right? Numerically. By the way, if you ever want to know what the label is on force, they have some specific labels. But if you think of the mass was in kilograms, the velocity is in meters per second, and the radius was in meters, right? So if you square things, you get meters squared over seconds squared divided by meter. One of those meters is going to cancel out with that. So that's meters times kilograms divided by seconds squared. That's kind of a weird label, isn't it? All right. If you take a look, let's go to the internet here real quick. I was trying to do that. Oh, there you go. That's what's known as a Newton. All right. A Newton is a measure of force, and it's 1 kilogram per, excuse me, time meters per second squared. Divided by second squared. Obviously, it's a lot easier to say Newton than it is to say kilograms times meters divided by seconds squared, right? So the measurement of force that we're actually dealing with is newtons. This is not something you're going to be tested on, or not even going to even be in the bonus homework, but I just wanted to point that out, that measures of force are often in newtons. Okay. So this is 8,000 newtons in this example. Newton, obviously named after Isaac Newton. So. Now, lastly, we've seen this formula before, and this one was one that was given to us. Obviously, we kind of looked at how it was derived, how we got to it, but still, it's basically a formula for calculating the amount of annuities and we've used it before. Remember, P stands for payments you're putting in each time, or principals, lots of those. R is your interest rate, M is how many times it's compounded, T is the number of years. M is how many times it's compounded per year, T is the number of years. So we did problems like this earlier. I'll just kind of walk through this. We put in $270 each month. So I know my P is going to be 270, and I also know my M is going to be 12, because we're doing things monthly. We earned an interest rate of 6%, so that means my R is going to be 0.06. How much would we have in the account after 14 years? That means my T is going to be 14. So this was a given model we had dealt with before. And all we have to do is plug in the right numbers into the right spots. Remember, when you're doing this, again, I like to multiply the 12 times 14. That gets 168. So when I type it in, what I do is I type in the whole numerator. So 1 plus 0.06 divided by 12 to the 168th power, and then I minus 1. I like to enter there. And then I divide by this number. Make sure you're dividing this. When you're dividing this, you divide it but you put this thing in parentheses. So divide by, in parentheses, 0.06 divided by 12. And then multiply by 270. And you should get that the amount you have after 14 years is $70,822.29, rounded to 2 decimal places. Is that all right? So again, that's a given model. We were given this. We didn't have to derive it on our own, although we did kind of see where it came from when we got to that point. I'll skip example 4. Example 4 was about half-life of plutonium. Kind of already done one of those with a given model. And so that's the end of chapter 7. That is the end of chapter 7. So chapter 7 was algebraic models. And we either built them or were given them based on the information in the problem, based on how the situation worked. Okay. Chapter 8 is about regression. And regression is another way to do modeling. It's basically, we're going to do modeling via data. So instead of looking at, well, this situation has to work this way, and therefore I can build a model of it, we're going to say, let's look at some data. We're going to determine if there looks like there's a pattern in this data, and then build a description of the model. And then obviously use the model. So that's the big idea with regression. Now, we're going to do some regression with the same function types we had, although not so much emphasized on the rational, but with linear, with exponential, and with quadratic. All right. Now, the data that we're going to use are going to primarily come from scatter plots. All right. So when I say we're going to look at data, we're going to look at pairs of data. And those pairs of data create points. So for instance, if I looked at me as an individual and I plotted out my height and weight on a graph, I could plot out my height and weight using an X value of height and a Y value of weight. And then I could do that for any other human being too. I can plot out their height on the X and their weight on the Y. And if I plotted out enough people's height and weight, I get a lot of dots. And that's the thing that we're going to look at with the scatter plot. So here's an example. Let's say I'm measuring something. My x variable on my first object is a 1, and the y variable on that first object is a 1.8. So what we have here is the ordered pair 1, 1.8. I can plot that on an xy axis. My next ordered pair is 2, 2.6. I can plot that on the xy axis. 3, 4.1, I can plot that. And so we plot a bunch of points. Now, eventually we're going to look and see if there's a pattern there. But I don't want you to get thrown off. My x doesn't always have to be just 1, 2, 3, 4, 5, 6, 7, 8. My x, I might have, if we're doing heights and weight, there might be somebody who's exactly the same height as me, but a different weight. So we can have like multiple points and on the same height. That makes sense. And multiple points on the same weight, so on and so forth. But ultimately, we're looking at a scatter plot like this, and we're saying, does there seem to be a pattern with those dots? In this case, there does. It looks like as you move to the right, the dots are also moving up. So as we move to the right, it looks like the dots are moving up. And while it's not going to be a perfect straight line, it looks pretty much like a straight line. Okay. And that's what we're going to do. We're going to say, look at these dots. What does the pattern of these dots look like? Is it going to look linear? Is it going to look quadratic? It's going to look exponential. It's going to look rational. In this case, it's linear. I'll talk about that. Why? Yeah, a little bit later. Once we get saying, oh yeah, these dots look linear, then we're going to use technology to build a model. Right? And it's going to build the model that best fits those dots. You can do this with Excel. You can do this with a calculator that has some functions. You can use other software too. But if you did this by hand, it would take a while. Right? There's a lot of calculations. So it's much nicer to use technology to build these models than to try things by hand. And then once we have the equation, that equation is just going to be a y equals, well, in this case, it's going to be y equals 1.4833 times x plus 0.025. Okay. So once we have that equation, it's like I have a given model now, and I can use that given model, the one that was given to me by technology. All right? And therefore, we can solve problems with this model that we've gotten through some technology piece. All right, so once we have the model, we have the algebraic equation, and then it's just like the previous chapter. Okay. Now, because we're building these models with data, instead of just building them based on logic and circumstance, we always have to understand the downfalls of building our model with data. All right. So we have to understand, for instance, how well the model actually fits the data and how accurate the model will be at doing predictions. And then what are some assumptions that people make that could be problematic if we have this model? So we'll talk about some of the problems to watch out for when we do this as well. All right. So the basic piece is we're going to be given data. Those data are going to produce scatter plots. We're going to ask, what pattern is this? Once we see the scatter plots, what pattern is this? And then we're going to say, well, what model, therefore, does my tech tell me it's going to be? And then we can use it algebraically, looking out for some problems. So that's the essence of chapter 8. Okay. The essence of chapter 8, using scattered plots to build models. And then using those and understanding how well they fit to the data, understanding what could go wrong. So let's start out by just reminding ourselves of some function types. All right. Now, again, we're going to keep it consistent with the last chapter. We're going to look at linear, quadratic, exponential, and rational models. Okay. Remember, linear models, linear functions, are ones that look like y equals mx plus b, or function equals mx plus b. Y equals mx plus b, f of x equals mx plus b. Now that's the algebraic stuff that we dealt with last time, meaning in the last chapter. This chapter, we're going to focus on the graphs to start out with. If we have a y equals mx plus b, no matter what the m and the b are, it's going to produce a straight line on a graph. So if our data looks like, in general, a straight line, that's probably going to best fit with a linear function. Does that make sense? Here I have graph y equals 2x minus 5. Am I right with that? So linear graph, straight line. Quadratic functions or quadratic equations algebraically look like y equals ax squared plus bx plus c, where a, b, and c are real numbers. Again, we saw that in the last chapter. That was the algebraic part of it. It turns out, if you have a quadratic function, the graph is known as a parabola. Now, this is a parabola that's what I call pointed up. Y equals x squared plus 2x minus 5. Here's a graph that's pointed up. So linear functions, graphs are lines. The quadratic graphs are parabolas. And like I said, the parabola that was graphed here was what I call pointed up because it goes up forever. Does that make sense? You could also have a parabola that's pointed down and that goes down forever too. So linear graphs are lines. They could be, any type of line you wanted. That work? Graphs are parabolas for quadratic. Graphs are lines for linear. Now the exponential functions have this multiplicative growth. We have this variable in our exponent. We saw, for instance, a couple of different exponential functions that compounding m times every year, compounding continuously. Y equals a times b to the x power. So we saw that algebraically in the last chapter. Exponential graphs don't have any specific terminology. So the graphs, we just call them the graphs of exponential graphs, all right? The graphs of an exponential equation is an exponential graph. But it does this, where it starts out kind of flat, and then it really shoots off. Okay. Now this is exponential graph, which is increasing. If it were decreasing, it'd just be flipped. All right. So the graph, the exponential graphs start out pretty flat, sort of slow growth, and then all of a sudden, they do that. Okay. Notice it's not like a parabola because this left-hand side never comes back up. With all that, this just stays flat, basically. That's the increasing exponential graph. The decreasing exponential graph does the exact opposite. It's like the mirror image. If you went to the left, it'd shoot up, and if you went to the right, it'd flatten out. We okay with that? So that's what the exponential graph does. Now, all exponential functions can be rewritten with base e. Remember, we talked about this earlier, but E is this special growth number associated with natural growth in math. It's about 2.71828. And when we deal with exponential functions in this class, and we ask, the reason I bring this up is that certain technologies, when they write their exponential function, will naturally write them in base E. Right? So certain technologies, when you ask for an exponential function, will write it in base E. And this is still just an exponential function, but that's the natural thing to do. Lastly, rational functions that are written in this way. Again, we're only looking at the one type in this course, the linear divided by linear. These are interesting in that they have limits. So if you graphed 30x plus 1 divided by 3x minus 4 is equal to y, you would get this one. Notice that as you move to the right, the graph is getting closer and closer and closer to 10 as the y value. So the further off I go to the right, it looks like the y value is approaching 10. Also, it turns out, if you move to the left, you get the y value approaching 10. So it has this limit. Notice also it has sort of two sides. It has the right-hand side, which goes up to infinity in the y value. And then as it goes to the right, it gets closer to 10. And the left-hand side, which kind of starts at negative infinity at the y value, and then moves to the left and gets closer and closer to 10. Does that work? So it's got these two sides. So graphs are rational. I didn't do that very well. Flatten out a little more. So the graphs look like this. They have these two parts. Okay. They have these two parts. Right hand and left hand part. And it turns out, if you drew a plus sign on all these rational graphs, it would kind of look like one side of the rational graph is trying to get to two parts of the plus sign, and the other side of the rational graph is trying to get to those two parts. Again, this is only for the ones we're talking about right now, which are linear over linear. Okay, not all rational functions look like that. They're not linear divided by linear. Is that right? Rational functions look roughly like that. So let's take a few minutes and identify graphs just based on the picture of the graphs themselves. All right, before we get into the looking at the data, looking at the scatter plots, let's identify graphs based on the pictures. So if you look at this picture of the graph on the left, and then look at the picture of the graph on the right, we should be able to identify the type of graph on the left and the type of graph on the right. The type of graph on the left, the one that's in green there, that's pretty obviously a straight line. And therefore that's gonna give rise to a linear function. So that's a straight line, therefore it's a linear function. On the right, well, we see those two distinct parts that are, again, if you drew a plus sign, they'd be getting closer to each side. So that looks like a rational graph. So on the left, that's a linear. On the right, that's a rational. That's all we're saying right now. Well, if you look at these two graphs, the one on the left looks like a parabola pointed down. Therefore, that's a quadratic model. So the one on the left is a quadratic model. And the one on the right, well, that's a classical exponential model. We start out really, really slow and flat, and then as we move to the right, we're increasing at faster rates. So that's an exponential model on the right. Take a look at those two. Just in your own head or write down on your notes what types of graphs these represent. These are the graphs of what kinds of models. Well, it should be fairly straightforward. On the left, we have a parabola pointed up, so that's quadratic. Going to be a quadratic model. On the right, we have a straight line. That's going to be a linear model. So quadratic model on the left, linear model on the right. Let's look at one more of those. We got pairs of graphs here. Well, on the left, we have the graph, again, it's kind of that classical plus sign. On one side, we're approaching two parts of the plus sign. On the other side, we're approaching the other two parts of the plus sign. This is a rational graph on the left. There's a rational on the left. And on the right, that's the classical, once again, exponential. The rates aren't always the same. The rates are actually decreasing this time as you move to the right. So this is the exponential, where essentially instead of growth, we have decay. So this is exponential decay. Because as you're moving towards the right, it's getting smaller and smaller and smaller. So left is rational, right is exponential. Now, identifying what type of function based on the look of the graph, I hope is fairly straightforward. Okay. It becomes a little bit more difficult once we get to scatter plots. All right. becomes a little more difficult once we get to scatter plots. Because it's not quite as obvious always what pattern we have with the dots. So here's an example. So here is the United States debt in billions of dollars. And this is since the year 1980. So 0 stands for the year 1980, 5 would stand for the 1985, 10 would stand for 1990, and so on and so forth. If we created a scatter plot out of these data, we would get this look. Now, if you looked at this scatter plot, it's not quite as easy to tell, but if you notice these first few dots to dots aren't as big of a jump as these last dot to dot jumps. Does that make sense? So it starts out a little bit slower and then starts getting faster and faster and faster. I would look at that and I would equate that to something like this. That exponential function. It starts out, the fairly slow growth, and then it's sort of increasing the growth rate. All right, so it starts out a little bit slower, and then it increases the growth rate. So I would say that probably looks most exponential, most like an exponential. Now, somebody else may have a slightly different interpretation of that data, but I would say exponential. Is that right? Most people would say exponential. I shouldn't say just me. Most people would say exponential. So we'd say that scatter plot looks most like an exponential scatter plot. And so what we will do in the next part is we'll say, since that looks exponential, let's fit an exponential model to it. And then we'll get our technology to fit that exponential model. Right. Here's another example. What we have here is a study done on blood alcohol level after subjects drank a certain number of beers. So a subject would drink, let's say 3 beers, and then 2 hours later, the blood alcohol level was 0.04. Somebody else may drink 3 beers, and 2 hours later, their blood alcohol level is 0.06. Everybody get the experiment that's being done here? So drinking a certain number of beers and then testing your blood alcohol level a couple of hours after that. Or maybe it was 1 hour, I can't remember the specifics. Okay. So here are the data. When you plot those points, it looks like this. All right. Now this one's a little bit different from the first couple we looked at. The first couple we looked at didn't have repeating points at certain values. This one does. If you look at the value of 3, people drinking 3 beers, there were 3 subjects that drank 3 beers. And their blood alcohol level was different for each one of them. So there's 3 different dots there. at this, it doesn't look quadratic because it doesn't look like it goes down and then back up, right? So it doesn't look like a parabola shape. It also doesn't look rational because we don't have that, the two different pattern shape. So we basically have a choice between linear and exponential here for our choices. Does it look like as we move out towards the right, does the speed of increase change? Does the rate of increase change as you move out to the right? To me, it doesn't. To me, it doesn't. I can draw essentially a straight line from this point to that point. And sort of get what I want. One way to think about this, let me enable editing. Let's see if I can go to this fantastic app called Microsoft Paint. There we go. Got it. One way to think about this is if we drew, I'm trying to think of the marker. If we drew a line, but we drew it really, really thick, okay? Could we get most of the dots? Yeah, we'd be really close to getting all of the dots if we drew one line that's really, really thick. Maybe I'll even draw it thicker than that. Draw a really thick line. Are the dots encased inside of that? Say, yeah, if you drew a thick enough line, looks like all of our dots are going to be encased inside of that. Does that work? And also, the other thing is that if you look at kind of where the dots are, some of them are going to be at the top part of that line. Some of those are going to be at the bottom part of that line, right? They're kind of all over inside that line. Okay. There's no real pattern inside the line. You guys see what I'm doing there? So if you drew a thick enough line, you get all the dots, and the dots kind of look scattered inside that line. Is that right? So I would say that looks linear to me for those reasons. Does that make sense? This looks like a linear pattern. All right? So when we build the model, when we build the function, we'll build a linear function based off of those data. Here's another example. I have these data as ordered pairs. 0 is 22, 1 and 7 is an ordered pair, 1, 4 is an ordered pair, 2, 0 is an ordered pair. If you graph this out on a scatter plot, which is in your notes, you get this. And I would say this is the classic parabolic shape. All right. This is the classic, oops, parabolic shape. Let me explain why. Again, I'll try to. There we go. I don't want that brush either. Yeah, there we go. If you look at this shape, it starts out up and then it goes down and then it's going back up, right? Now, this is the thing to note, that in this parabolic shape, it doesn't matter that the left side and the right side didn't go up equal amounts, right? If I would have extended this pattern, it probably would have went off to who knows where. So it's okay that we're going down and up because we're just tracking like one section of the parabola there. Everybody get that? So we're tracking like a part of the parabola, not the entire thing. And so because that looks parabolic shaped, I would say, oops, hit the wrong button. I would say this is going to be a quadratic function. So that's a quadratic function. Example 7, that is. Let's look at another scatter plot. Now this is just random data that I've put in. X is 0.5, Y is 5. When X is 1, Y is 8. When X is 1, Y is 4. So we're getting lots of different points. If you drew this scatter plot, you get this. Now, this is the last thing I'm going to say. If you look at these data points, if you look at these points, does it really look like a line? Probably not. Doesn't really have that going down and then back up or up and down feature that a parabola has. Probably not parabola. Doesn't really look like a rational function because it doesn't have those two sides either. It doesn't look like exponential because it doesn't go flat and then up, right? Kind of increase the speed at which you're increasing. So what I would say is this doesn't look like anything. This looks like just a random splattering of dots. And that is possible as well. It is very possible that you get to scatter plot and it really doesn't have a pattern, at least not one that we would recognize. So it's perfectly fine to get, if you get to a place and you see a scatter plot like this, to be able to say, this is not one of those functions we looked at. So there's no pattern at all here. That's going to be one of your options of identification when you get to the homework. When you get to the 8-1 homework and you're identifying functions, one of the options is gonna say, it doesn't look like there's a pattern here. And that is perfectly all right. So we have our 4 standard functions. The linear function, the quadratic function, the exponential, and then the one type of rational we're looking at. But then there's this implicit 5th scenario of the scatter plot, which there doesn't seem to be a pattern, right? And that's perfectly fine. It's perfectly fine to say there's no pattern here. No pattern there. Does that make sense? All right. Now, I think what I'm going to do is I'm going to stop here. We've covered 8.0 and 8.1, identifying the functions. And then 8.2 will be all about creating the regression models. Okay, but that takes a little bit of time. And since we're kind of close to the end of class time, I don't want to get started on something that we can't really get into. But we're going to use technology to do that. We're going to use our calculators, or more likely Excel. And I'll talk about how that's going to work in the homework and those things. But we'll do that next time, okay? Don't forget, since we're done with chapter 7, make sure you finish those homeworks. Chapter 7 by Friday at 5. And then other than that, I will see you all next week.